Okay, hello everyone. Um, Wanted to share a little experiment with you all to get started today. Um, First, let me ask any technical or administrative questions that you might want to bring up. I am trying to use multiple screens better today. I have the gallery on a separate screen successfully. I did put the course meetings on the catalog, and oh, let's see. I'm using the wrong camera for the moment. Let's see if I can do this. Okay, there we go. So I want to quickly share with you a little experiment. So when we're dealing with the measure theory on a Lie group, there's always an invariant measure, or at least a right invariant measure in the non-abelian case, called Haar measure. And in the case of the real line, Haar measure is ordinary Lebesgue measure. In the case of the circle, it's ordinary linear measure on the circle. What is it in case of the multiplicative group of the real line? In other words, the real numbers with 0 removed. It's the measure, which I'll put in the chat, dx over x. So there's this measure has the property that if you multiply x by a, it goes to the measure dax over ax, which is of course equal to the same measure. So when we're dealing with quantities in a multiplicative context, it's often this measure dx over x that is most important. And for example, if we're looking at all of the real numbers, but we only care about them up to a multiple of 10, which means we only care about how their decimal expansion begins, for example, asking what the first digit is, we're really working in the group R star, a modulo 10 to the z, which I'm writing in the chat. And this multiplicative measure, dx over x, descends to a natural measure on that quotient space. And that's the measure that assigns 30% to the set of numbers whose first digit is 1. So what I want to mention as a sort of cultural aside is something called Benford's law, which says that in lots of natural settings, when you look at data, the numbers beginning with 1 occur much more frequently than the numbers beginning with 9. In fact, the numbers beginning with 1 occur with 30% of the time, and the numbers beginning with 9 occur at most 4%, around 5% of the time. There must be some way to make money off of this observation, or the fact that people are ignorant of it. I don't quite know how. But one reason you might imagine that this has to be true is that if you are measuring numbers in units, for example, miles or kilometers, and there is some distribution of the digits, well, that distribution should be independent of the units that you're using, which means that it should be invariant under multiplication by the ratios between the units, which means it has to be this measure on the multiplicative circle, because there is only one invariant measure on that circle. So just to give a quick test of this, I grabbed a random table off of the internet of distances between towns in South Africa, and I just highlighted all of the distances which are given in kilometers that begin with 1. You can see them in yellow here. I hope this screen is being successfully shared. Can everyone see? Carl, can you see the table?
Yeah, looks good.
Okay, and now let's look at the ones that begin with 9. So it's an interesting amusement to try to find other data on the internet which exhibits Benford's law. Sometimes when financial documents... Yes, louder?
But if we can...
Sorry? I couldn't hear that. Can you please repeat? Was there a comment? Okay, sorry, please speak again or raise your hand if there is a comment. So I was just saying that when people forge financial information, they usually don't pay attention to Benford's law, and it's sometimes used by forensic detectives to tell when information is not coming from real life. Okay, so a quick aside on the exercise regarding, yes? Regarding 2. Okay, so let's switch now to the Blackboard. Okay. And let me switch to speaker view in my gallery. Okay, so so today I want to start the study of ergodic theory proper and prove some general theorems. Let me first, though, say give one more example of a way of producing measure preserving maps, which I think will be familiar or important to many of you, because a big topic these days is symplectic geometry. So if one has, let's say, M2N, let's say this is a compact smooth manifold, a symplectic form on M is a closed 2 form. So omega is a smooth de Rham 2 form. B omega is equal to 0, and it should have the property that omega to the n is a positive volume form on your manifold. So it determines a measure, a finite measure. We take this to be our measure M. We take the manifold to be our space X. And then we get a flow on X rather than a single transformation. It still fits nicely into the ergodic theory we've discussed, which preserves this measure M. For any function, h, smooth function, from x to the real line. This is called the Hamiltonian flow associated to h. And it has the property that it preserves the level sets of h. So h is constant along all of these flow lines. And the way it works is from h, you get a vector field, v of h, which is uniquely determined by the property that when you pair v of h with any other vector w, using the symplectic form, what you get is just the value of dh applied to that vector w. In other words, you get the derivative of h in the direction w. And then it's easy to show that the Lie derivative of, so another way to write this is that the contraction of omega with v, we call it v for brevity, is equal to dh. And then it's easy to show the symplectic form is preserved along this flow. If you know your formula for Lie derivatives, the Lie derivative of omega with respect to v is ix d omega plus ix omega. And let's see, so dix omega is d of dh, so this is equal to 0, and d of omega is equal to 0 because the form is closed. So that's the idea of a Hamiltonian flow. If in the very simple case where M is a surface, for example, if it's say R2 mod Z2, then this function h has some level sets. And what happens is you basically take the gradient of h, which is maybe bigger here than it is there, and you rotate it by 90 degrees so it becomes parallel to the level sets of h. And then you get a flow on your surface, which is slow when the level sets are far apart, and then it speeds up when the level sets come closer together. And in that way, it preserves volume. And another paradigmatic example is to take M2n. Well, this won't quite be a finite volume yet, but you take it to be the cotangent space to some other manifold n. The cotangent space of a manifold carries a canonical symplectic form. And then maybe this manifold n is actually a Riemannian manifold. So you can measure the lengths of vectors or of covectors. And then your function h might look something like h of an element of the cotangent bundle. Well, the cotangent bundle via this metric is isomorphic to the tangent bundle. So think of h as being something you apply to a vector and adjust the length of this vector with respect to the metric. And then the corresponding flow of the tangent bundle is what's called the geodesic flow. And by the way, for people who are thinking in terms of classical mechanics, here the Hamiltonian is the kinetic energy. It's the velocity squared. So if you were on the cotangent space of a surface, you pick a vector at some point, then this vector under this Hamiltonian flow is just transported along the geodesic it generates. It's parallel transported. And since the function h is preserved, the length of this vector is also preserved. So in studying geodesic flows, one usually restricts to, say, the vectors of length 1. That's a level set at h. And then studies the behavior of this flow on the unit tangent bundle. Okay, so that's another source of measure theoretic dynamical systems. Now, before we start studying T from xm to itself in general, I want to make a remark on how many possibilities are there for xm as an abstract measure space. So often, for example, if we're studying flows on manifolds, we have to first confront the fact that there are infinitely many different manifolds. But it turns out that in measure theory, there's really only one measure space or one probability space of interest to us. And that is the interval from 0, 1 with the usual Lebesgue measure. So an example of a measure space is the interval 0, 1, and I'll write dx for Lebesgue measure. This is, of course, a probability space. Here, let's also assume we have a probability space. Almost all the probability spaces that you encounter in real life are isomorphic to the interval from 0 to 1. So what do I mean by real life? Well, let's take, for example, a surface with some area measure on it of total mass 1. I claim that this surface of genus 2 with total area 1 is isomorphic as a measure space to the unit interval. So why is that true? Well, what you can imagine is you first take this surface and you cut it up into lots of little pieces, and then you reassemble those pieces to form a square. So maybe you have to be very clever to get that to work, but you're allowed to use infinitely many pieces. So since you have measure 1 on both sides, it's kind of believable. You can cut and paste this to form a unit square. And then you observe that the unit square is isomorphic in a measure preserving way to the unit interval. And that's because you can take a point xy in the unit square and send it to the point whose, say, decimal expansion is x1, y1, x2, y2, etc. And this is a measure preserving map, even though it's highly discontinuous. So there's almost, one almost always works with measure spaces which are reasonably small, say they're sigma finite, and such spaces are almost always isomorphic to 0, 1 if they have finite total mass. If they have infinite mass, they're almost always isomorphic to the real line, or the interval from 0 to infinity. So there's really only one space to work in. Now that's not quite true, because there's one other measure space that's of interest, which is a finite or countable set with some positive masses on each of its points. For example, Z mod n with Haar measure is not isomorphic to the unit interval. But that's very different from the unit interval. It has atoms, that is single points of positive mass. And so one also might consider, in addition to a space that looks like the interval, you might take only part of the interval, and then you might take union a finite or countable set of atoms. And the measure spaces that look like this are called standard Lebesgue spaces. So I just wanted to take this moment to say that although some of what we will say is true for arbitrary measure spaces, most of the time we'll be thinking in terms of standard Lebesgue spaces, and usually we won't even have these atoms to worry about, except for example, when we look at Haar measure on Z or Z mod n. Okay, now what's an example of a non-standard Lebesgue space? So there's something called white noise. White noise is supposed to be like a random function on the real line. How can you make a random function on the real line? Well, the naive approach is to do the following. You first choose some distribution on the real line, say the Gaussian distribution. So we choose some probability measure, M on R. And then we define a function f from R to R by choosing the value of f of x is chosen at random with respect to M for all x independently. So if you want to build this function, it takes a lot of time. You have to go to each point on the real line, and for that point, pick a point at random on the real line with respect to whatever measure you've chosen and assign that value to your function. So there's uncountably many flips of the coin that have to be performed to construct this function f. Nevertheless, this f resides in the space of all functions from the real line to itself, which is just the infinite product, R to the R. And so we can think of that as our probability space. And then our measure is just the product over all elements of R of this measure that we fixed at the beginning. By taking it to be the product measure, we ensure that the coordinates are chosen independently of one another. And this is a huge measure space. It is not a standard Lebesgue space. This is the kind of thing we will try to avoid in this course. And if you want to entertain yourself a bit, here's an exercise. If you tried to take this as your definition of white noise, you would run into certain problems. For example, a random function would almost certainly be non-measurable. So f is almost certainly a non-measurable function. Okay, so that's just to briefly mention a pathology that we are going to avoid. Okay, well, since this was pathological, get rid of it. And now let's start by proving the most fundamental theorem about measure-preserving transformations. And this is really the difference between measure-preserving transformations and transformations that don't preserve measure. So a transformation that preserves measure is, for example, the equations that govern the motion of a frictionless pendulum. It just keeps going back and forth. An example of a transformation that does not preserve measure, it actually shrinks measure, is a pendulum with friction. And it just slowly dies down and reaches this equilibrium position where it's no longer moving. What's the difference? What's the qualitative difference between those two dynamical systems? So let's specify our setup again. So Xm will be a probability space. I'm not going to emphasize the sigma algebra that should be here. All the sets under discussion will be assumed to be measurable. And then T from X to X. And now for concreteness, and just to simplify things a little, I'm going to just require that this is an invertible measure-preserving transformation. So for any set A that is measurable, the measure of A is equal to the measure of T of A, and it's also equal to the measure of T inverse of A. Okay, so the first theorem really in measure theory, which goes back to Poincaré, is that T is recurrent. And what this means is that for any measure, so A with the measure of A positive, of course, I'm implicitly assuming A is measurable, so it has a measure. Actually, I don't even have to say the measure of A is positive. For any set A, almost every X in A returns to A infinitely often. By this I mean, we draw a picture of our space X and our space A. If you start with a point in A and apply T, you may very well go outside of A, but eventually you'll come back. And in fact, once you come back, you can start over again, and then you'll come back again, and so on. So this is called Poincaré recurrence. And you'll notice that the pendulum with friction is not recurrent. There's a positive measure set of starting positions for the pendulum where it decays down to this fixed non-moving point. It doesn't come back to where it started again. But the frictionless pendulum does. And Poincaré was motivated to prove this theorem when studying the three-body problem in celestial mechanics. So we all know the two-body problem with Newtonian gravitation can be solved exactly. The orbits are ellipses, assuming you have point masses. But the three-body problem has no closed form solutions. So what can you do? Do you just give up? Well, not everything in math has to be done by formulas. And so what Poincaré observed is that if you think of the evolution of the solar system as a measure-preserving transformation on phase space using the Hamiltonian formalism we just mentioned, then it has this recurrence property. In other words, whatever the positions are of Mars, the Moon, Jupiter, and Saturn, which are rather close together in the sky right now, whatever we see today, if we wait long enough, we'll see the planets in approximately the same position over and over again infinitely many times in this idealized world of frictionless dynamics. Now, unfortunately, that's not quite true. Even that proof doesn't really work. And the reason it doesn't work is that the measure space for the solar system is not a finite measure. The planets can, in principle, get arbitrarily far apart. Also, their velocities can get very high if planets come close to each other. So this doesn't quite prove the statement that I mentioned. Nevertheless, it's a basic property that you see when you have a finite measure preserved. For example, if you go back and look at the picture of a K3 surface I showed last time, there were some elliptic islands. In those elliptic islands, the map is like an irrational rotation, which is of course recurrent. There's also this stochastic C where the orbits look like they're random. Well, in that random regime, you still have recurrence. Even though you don't have periodicity or quasi-periodicity, you still have recurrence by Poincaré's theorem. Whenever you have a measure that's preserved, you have recurrence. Okay, so the proof of this is very easy. We let B be the set of X and A such that Tx, T squared X, etc. is not an A for all n. Let's say n greater than 0. So if the forward orbit does not return to A, those are the bad points, the points for which this theorem fails in the sense that the point doesn't even come back once, let alone infinitely often. So we have our set A again, and now we have this bad set B. And B has the property that, let's call that B0, we let Bi, Ti of B, B. It has the property that B1, B2, etc., they never intersect A again. They spend all of their time outside of A. And these sets all have the same measure. But now, could these sets overlap? So suppose you were to have Bi to overlap with Bj, in the sense that they meet in a set of positive measure. Well, if that were true, you would then be able to conclude that if Bi meets Bj, let's say I is bigger than j, then Bi minus j meets B0. But B0 is contained in A, just by applying the inverse of the map j times. So if these meet in positive measure, then these meet in positive measure, and that's a contradiction because we're assuming all of these guys are outside of A. And so these B's are disjoint, and they all have the same measure. So the sum of the measures of the Bi's is less than or equal to 1. And since they all have the same measure and they're disjoint, this implies the measure of all of them is equal to 0. In particular, the measure of the first one was equal to 0. So that shows almost certainly a point comes back into A. And then it's almost obvious that it can then start over and it still has to come back into A. And so in fact, you get infinitely many returns. Another way to prove you have infinitely many returns, which is a good technique to know in ergodic theory, is that if T is measure preserving, then T to the n for any large n is also measure preserving. And so if we apply this argument to T to the n, we find that there is some inward of T to the n that brings X back into itself. In other words, X returns after time capital N to A for almost every point in A. And since we could choose n arbitrarily large, there must be infinitely many returns. Okay, so that is the recurrence theorem of Poincaré. Now there's another statement that is also interesting. You might ask, well, I'm imagining some position of the planets, and I wonder if that position will eventually occur if we wait long enough. We might have to wait an enormous amount of time, but will every possible configuration of planets occur? And of course, that might not be true. It might be that there are two different regimes for the solar system, and in one regime, these good positions occur, and the other regime, only bad positions occur. But if the state transformation is ergodic, then you can't split the space in that fashion. And so we have a similar theorem which says that if P is ergodic, then for almost every x, and let's say the measure of A is positive, then almost every x in X returns, or enters, I guess I should say, since it's not starting there, enters A infinitely often. So the orbit, even if it doesn't start in A, has to visit A, and it has to come back over and over again. That's quite easy to prove. If you take the set of points that never enter A, well, that turns out to be closed under the action of T, invariant under the action of T. And by ergodicity, it has to have either full measure or zero measure, but its complement contains A, so it has to have zero measure. Okay, so these are what I regard as sort of the easy and, essentially trivial theorems of ergodic theory. But they immediately suggest what is probably the most fundamental basic question, which is, if this orbit is going to come back to A, how often is it going to come back? How long do we have to wait? What amount of time does it spend in A? And that is called the basic ergodic theorem. And that we will spend some time proving this. We will prove it in a couple of different forms. So this is the basic ergodic theorem. It says that, so we suppose P is ergodic. Then, for almost every x in X, if we look at the set of n greater than or equal to 0, let's say between 0 and capital N, such that Tn of x is in A, that's the amount of time that this orbit spends in A, and we divide by the amount of time that's passed, that this ratio converges, as you would guess, to the measure of A. So the amount of time spent in A is proportional to its measure. In other words, almost every orbit is uniformly distributed. We'll talk about uniform distribution more systematically very shortly.
Kurt, can you add a cardinality sign?
Thank you. You cannot divide a set by an integer. Yes, the number of times x visits A divided by the amount of time that's passed converges to the measure. Now,
Kurt,
yes.
Kurt, are we assuming that ergodic transformations are always measure preserving? Like, is that part of our definition for ergodicity?
That is not part of our definition, but it's part of our setting.
Okay.
So here, I've actually implicitly assumed that T is both measure preserving and even invertible, which it doesn't have to be. Like the squaring map on the circle is measure preserving, but not invertible. For simplicity, I'm sticking to this situation. For everything I'm going to say about this kind of ergodic theorem, measure preservation is absolutely essential. However, as you bring up, ergodicity makes sense even for transformations that don't preserve measure. This definition of ergodicity in this broader setting is just if you split the space into two invariant sets, one or the other has measure 0. But we will, to get these quantitative theorems, we absolutely need measure preservation. Other questions? Okay, so I hope I've given you enough examples of measure preserving transformations to convince you that the set of T satisfying this axiom is non-vacuous and contains lots of interesting and complicated maps. Okay, so let me state this, as long as we have the basic ergodic theorem, let me state some more precise variants of the ergodic theorem that we will eventually prove. So the variants will start with a measurable function to the real line. And they will consider these sums, which we wrote down before, we pick a point x and we average f over the first n points in the orbit of x. So we take the sum from I goes from 0 to n minus 1 of f of t pi x. And then we can ask how these sums behave for functions. And there's two theorems. And the one I hope to get to today is, I'll call this the L2 or von Neumann theorem. And it says that if f is in L2 of x, always with respect to this measure m, which I may drop to shorten the notation, well, let me put it this way. If f is in L2 sorry, let me state a couple of versions of this. If f is in L2 of m and t is ergodic, then Sn of f converges to the constant function, which is the integral of f with respect to our measure m. This means the constant function in L2, period. So it says that these averages converge over the orbit, converge to the average over the whole space, as you might expect, because the orbit is being forced to sample the whole space by this theorem here. And then there's some variants of this. When I state the general version, there's also a version when f is not ergodic. And in that case, this function here will not necessarily be constant, but at least it will be invariant under the action of t. And then there's the Birkhoff-Hintschen ergodic theorem, which is significantly more difficult. And it says what happens not in L2, but for individual values of this function. And it says under the same hypothesis, including the hypothesis of ergodicity, that Sn of fx tends to the integral of f with respect to this measure m pointwise for almost every value of x. And here, we only need that f is in L1 of x. Slightly weaker hypothesis. And as I mentioned, both of these theorems will have statements that apply even when the map is not ergodic. Okay, so that's the direction we're headed. What do they have to do with the basic ergodic theorem? If you let f be the indicator function of your set A, so it's equal to 1, if x is in A, and otherwise it's equal to 0, then this quantity that I've written down here is just Sn of the indicator function of A, and the measure of A is, of course, the integral of f over x. So the more advanced ergodic theorem, the Birkhoff one, applied to the indicator function of a measurable set, gives the basic ergodic theorem. And the basic ergodic theorem is the heart of the matter. Okay. Any questions at this point? Okay, so I'm now about to reveal one of the big ideas in ergodic theory, which is already hinted at in von Neumann's theorem here. The big idea is that when you have a function acting on this measure space, that is kind of hard to visualize, but it gives rise to a linear map on L2 of x. So in modern terminology, there's a functor that turns a probability space into a Hilbert space, and then it turns an automorphism into an operator on that Hilbert space. And so we can then take everything we've learned about linear operators in our functional analysis classes and try to apply it to understanding not quite T itself, but this linearization of T. In much the same way as it might be hard to study a topological space, but you can try to study its homology. We'll lose a lot of information by going to the unitary operator, but we'll gain a lot of insight because we can actually analyze what that operator looks like. So this is the idea of spectral invariance of T. Okay, so again, my standing assumptions are that T preserves this probability measure and is invertible. And as I just mentioned, we have a functor that takes our measure space to a Hilbert space, which is L2 of X, in measurable functions that are square integrable. Okay, now, I mentioned that there are not that many examples of measure spaces up to isomorphism. They all kind of look like the unit interval. How many examples of Hilbert spaces are there? Well, let's impose a kind of tameness assumption that the Hilbert space is separable. Separable means that it has a countable dense set. For example, if X is a compact metric space, then the continuous functions will be dense here. The space of continuous functions is separable, and so L2 of X is separable. So let's assume that H is separable just for tameness. If this is the unit interval, of course, it's also separable. So if X is a standard Lebesgue space, this is automatically separable. This is a mild technical hypothesis. How many separable Hilbert spaces are there? Well, one example is, these will be complex Hilbert spaces, is C to the n, finite dimensional Hilbert space with the usual inner product. CW is the sum of CI/WI bar. Another example is little L2 of the integers. This means you have an infinite sequence of complex numbers indexed by the integers, and the norm of that sequence is the sum of the absolute value of its entry squared. That's it. Every separable Hilbert space is isomorphic to one of these. It's either finite dimensional or it's isomorphic to L2 of Z. And the reason is that a Hilbert space is uniquely determined up to isomorphism by the cardinality of its orthonormal basis. In the same way, a vector space is determined by the cardinality of a basis over the field. And in a separable Hilbert space, the orthonormal basis is either finite or countably infinite. And this is the case where an example where it's countably infinite, this is a case where it's finite. So every Hilbert space is isomorphic to one of these two. And of course, if X is a measure space, the finite dimensional case only is going to arise when when the measure M is atomic with finitely many atoms. So, so we'll really be interested in this case all of the time. Okay, so that's our functor. And now comes, of course, the interesting thing is not what our functor does to objects. I mean, that's mildly interesting. But more important, what does it do to morphisms? So if our category is measure spaces, we might take the morphisms to be just the isomorphisms of measure spaces. So bijections that preserve measure, that's what our T is. And so T will necessarily produce an automorphism of this Hilbert space, which I'm going to denote U. Of course, it depends on T. It's determined by T functorially. And U of F is just F composed with T. Just pull back L2 functions by T. And because of the fact that T preserves measure, this map preserves the inner product. So U is unitary because T preserves the measure M. By unitary, I mean UF, UG is equal to FG for all L2 functions. And in fact, since U is invertible, this we can write as U star UF G, and that's equal to FG for every value of G. So that says U star U of F is equal to F. So U star U is the identity, and therefore U star is equal to U inverse. That's the definition of a unitary operator. Okay, so we've taken our transformation T, and now we have some sort of operator in a Hilbert space. Let's think about this a little more abstractly. We started with T. Associated to T, we have the group generated by T and its inverse. And then this group acts unitarily, preserving the inner product on H, which is L2 of X, this Hilbert space. Now, this action might be ergodic. So from the spatial perspective, there's no way to reduce it, to make it simpler. On the other hand, provided H is infinite dimensional, a unitary operator can always be reduced. In fact, what are the irreducible representations of the integers? The only unitary representations of the integers that are irreducible, that have a non-trivial invariant that can't be decomposed into invariant subspaces, are the one-dimensional ones, as you're familiar with from abelian groups. So the more generally, so the irreducible representations of Z, and let me say unitary, since we're going to be dealing with infinite dimensional representations, are one-dimensional. In other words, they all consist of the maps like C goes to C by Z goes to lambda Z, where the absolute value of lambda is equal to 1. This condition means that length is preserved in this one-dimensional Hilbert space. So because of that, the action of T on L2 of X should, in fact, must decompose into a direct sum or direct integral of one-dimensional representations. And those one-dimensional representations are indexed by points on the circle. So from the representation theory of the integers, that is from the spectral theorem for a unitary operator, we'll be able to get new invariants of T, which describe exactly how it acts on this Hilbert space. But we will forget what the space X is in the process. So we'll have lost a lot of information, but hopefully some stuff will be left that will be of interest to us. Okay, but before we pursue the definition of these spectral invariants, let me show you how beautifully this L2 theory works. This was observed by von Neumann, and I'm sure that, as I'll explain when we look at the spectral theorem, von Neumann considered this to be a trivial theorem, what I'm about to state, which is now known as von Neumann's ergodic theorem. Often, the simplest theorem you prove is the one for which you're the most famous. So the theorem is this. Let's let U be a unitary operator on a Hilbert space S, H, and let's let HU be the set of F such that UF is equal to F. In other words, they're the vectors that are fixed by the operator U. Fixed vectors. And then we also will consider now, as before, we have Sn of F, which will this time be 1 over n, the sum from 0 to n minus 1 of Ui of F. So we can perform the action of T. We're secretly thinking that U comes from T, but in fact, the statement of the theorem will be true for any unitary operator. So we have these sums. And also, we'll notice that this space HU, this is a closed linear subspace of H. So there is a projection operator from H to HU, orthogonal projection. So we have a picture of our Hilbert space with this special subset HU. Now, by the way, when F is ergodic, how big is HU? Well, HU consists of the functions that are invariant under T. And if you have a function that's invariant under T, then say the part of the space where the function is less than A is invariant, the part where it's bigger than A is invariant. But since your T is ergodic, one or the other of those two spaces has to have zero measure. And so as a consequence, any vector that's fixed when T is ergodic has to be constant almost everywhere. And so when T is ergodic, HU consists of the constants and vice versa. So let me just put that as a little proposition here. HU is equal to C, by which I mean the constant functions on X, if and only if T is ergodic. So the invariant functions might well be very small. And in the ergodic case, the projection to the constants is easily defined. In this case, P of F would just be the constant function, which is the integral of F. So what we would hope is that in the ergodic case, Sn of F converges to this constant function P of F. Okay, so to approach this theorem, here's the one point where just a tiny bit of imagination is required. We have this orthogonal projection P. What I'd like to try to imagine is what functions are in the kernel of P. What functions go to zero under this projection? And one way to think about that is that HU is U invariant, and U is orthogonal. U preserves the inner product. So if you apply U to a vector, it still projects to the same point here. So PU is equal to P. Moving a function by U doesn't change its projection. So how about if we take a function and we move it by U, take it the same and take the difference. So these are what are called co-boundaries. And I'll define this as the boundary of U will be the set of F and L2 such that F is equal to G minus UG for some G in L2. And what you'll notice is that P of G minus UG is equal to 0. Now, going back to the case of measure-preserving transformations, this is obvious. What this boils down to is saying that the integral of G minus G composed with T with respect to this measure M is equal to 0. And of course, that's true because T is measure-preserving. The integral of G and the integral of G composed with T are the same thing. So these guys, these so-called co-boundaries, necessarily project to 0. They're part of the kernel of P. And of course, the kernel is closed. So it contains the closure of U. And then the theorem is that, in fact, the Hilbert space is the direct sum of HU and the space of co-boundaries. Now, why is that good? Why does that answer our problem? Before we prove that, let's see what happens when you start averaging a co-boundary. So if we take Sn of G minus UG, well, what happens is when you take Sn of G, you get the orbit of G under the first I iterates going up to n minus 1. So here you get 1 over n G plus UG plus ui minus 1, un minus 1 G. But then on this side, you start subtracting, and you subtract off UG all the way down to U to the I minus 1G, and then minus UIG. So the whole series telescopes, and you're just left with 1 over n G minus U to the UNG. There should have been n minus 1. And so, of course, the norm of Sn applied to this coboundary is then less than or equal to 2 over n times the norm of G in L2, which goes to 0. So coboundaries are good. They have the property that when you average them, they're annihilated, which they should be because they project to 0 in H of U, which they also should be by our idea for the ergodic theorem that G minus G composed with T is 0. Their average of a coboundary is always 0. So it's a terrific situation when the space of functions can be decomposed as invariant functions and coboundaries. Unfortunately, that is almost never true. It's not true that HU is that H is the direct sum of HU and delta U. And the reason is that delta U is almost never, I guess I should call that boundary of U, du, is almost never closed. You see, you might have a sequence of functions f converging here, and they're each written as coboundaries, but even though the f's are converging, the g's might be going to infinity. So this is usually not closed. But that doesn't matter, because you see, if you can take a function and approximate it by 1, for which the SNs tend to 0, then you're in good shape, because Sn applied to the difference between those two things is small. So let me remark at the very, should have made this remark at the very beginning, that the norm, that these unitary operators have norm 1 as operators. The norm of Sn, being an average of them, also has norm 1. So the norm of Sn in L2 is equal to 1 for all n. Equality holds because the constant functions are fixed by these. So if you know what Sn does to a function, then when you perturb it slightly, you almost know what it does to that perturbation. Okay, so I haven't stated the theorem yet, but I've given all the ideas in the proof. So the theorem is, let me fit it down here. So the theorem is that for all f in L2, Sn of f converges to the projection of f to the U invariant functions. And of course, what I mean by converges is it converges in the sense of norm. That's von Neumann's ergodic theorem. And as I mentioned, when f is ergodic, that implies that we're converged. The average is converged to a constant. And then the argument I just sketched shows that this theorem is implied by the following lemma. And the lemma is that the Hilbert space is equal to HU direct sum the boundary of U bar. So to complete the proof, we just have to prove this lemma. And the proof of this lemma is very easy because we've assumed that U is invertible. So the proof of the lemma, so what we want to do is just show that the perp of du is equal to HU. So we know already that du perp for any subspace of Hilbert space is the same as the perp of the closure. And we saw already that this is contained in, that this, let's see. Yes, that this contains the invariant functions. Let's show that in fact it's equal to the invariant functions. So if f is in du perp, then what does that mean? It means the inner product between f and g minus ug is equal to 0 for all g. But this is the same thing as saying, using adjoints, that the identity minus U star F inner product with G is equal to 0 for all G. And now we use the trick we always use in Hilbert space. The only way a vector can have 0 inner product with everything is if it itself is identically 0. So this is the same thing as saying F is equal to U star F, but U star F is U inverse. And so this implies F is an HU. Okay, so that's the proof of this deep ergodic theorem. It's actually extremely slick and simple in the case of L2 functions. Okay, so any questions on the development of the spectral approach at this point? So I should say that again, the notes for this course are a moving target. They're rapidly evolving, and I think you'll find a fairly complete treatment of this discussion there, as well as everything that I'm going to say going forward for the next couple of sessions. Okay, so now I wanted to use this unitary operator to get some invariance of F. And for that, I need to do a little review. So let's review the spectral theory of, and now you've probably heard the idea of the spectral theorem before. There are many versions. Let me say the most general version is of normal operators on Hilbert space. And what this theory does is it describes for us up to isomorphism the way various operators behave. So again, some terminology. A unitary operator, well, first I'm going to let B of H is going to be the set of all bounded linear operators. S from Hilbert space to itself. With the operator norm, it's actually a Banach algebra under composition. Unitary means you have an operator such that S star is S inverse. Self-adjoint, another famous class of operators, are those such that S star is equal to S. It's equal to its own adjoint. And then normal are the operators which include these two, and they're ones that have the properties that SS star is equal to S star S. In other words, the key to the spectral theory I'm about to formulate is that the operator S, together with its adjoint, generate a commutative subalgebra of B of H. And commutative algebras, like representations of the integers, can be decomposed into one-dimensional spaces. That's the idea. They all look like continuous functions on a compact metric space. That's the basic idea in the theory of Banach algebras, and especially C-star algebras. So anyway, let me take an operator, and let me define what the spectrum is of this operator. Now, normally, for, say, a finite dimensional operator, the spectrum just means the eigenvalues. But I need to put that in quotes because we may have elements of the spectrum which are not literally eigenvalues for the operator. There might not be any associated eigenvector. So we define it not by saying that it's the value of lambda such that lambda is an eigenvalue, but it's the values of lambda such that lambda times the identity minus S is not invertible. In other words, there is no bounded operator which inverts this difference. And it can be shown fairly easily that for a unitary operator, which is going to decompose into these one-dimensional subspaces, that the spectrum, let me call it U, well, I'll call it S. The spectrum of S is contained in the unit circle. In fact, the spectrum you can think of as satisfying see, if S were multiplication by a scalar lambda, this would say that lambda bar is equal to lambda inverse. That's a good heuristic for remembering what property the elements of the spectrum satisfy. Here, lambda bar would be equal to lambda. So the spectrum should be contained in the real line. In fact, it always is. And here, well, it can be anything, but it's always a compact subset of C. Okay, so the first invariant you can attach to an operator is its spectrum. And for these ergodic, these measure-preserving dynamical systems, the spectrum will be a subset of the circle. Unfortunately, the spectrum is almost always the whole circle. So this is not yet a good way to tell measure-preserving systems apart. However, there's more information you get for a unitary operator, for a normal operator. Namely, there's something called the spectral measure and the multiplicity function. So S determines a pair, mu m, where mu is a measure on its spectrum, and m is just a map from the spectrum to 0, 1, 2, up to infinity. And now here's the way this data works. From the data of mu and m, you can build a Hilbert space. So knowing this data, in fact, we can reconstruct S. This data is an invariant of S and it allows us to build S again up to isomorphism. If we forget what S is, but we remember this, then we'll be able to reconstruct it. And in the finite dimensional case, this should be familiar to you. This condition that S commutes with its adjoint, in the finite dimensional case, what that means is that if S leaves invariant a subspace, then it also leaves invariant a complementary subspace. So for example, once you find an eigenvector, the perp of that eigenvector is also preserved. And then you can find an eigenvector there. In the finite dimensional case, that'll let you diagonalize S. And in the finite dimensional case, this measure will be supported on the eigenvalues, and the M will just tell you the dimension of the eigenspace. And of course, that's enough information to reconstruct S up to isomorphism. In other words, S can be represented by a diagonal matrix where the elements in the support of mu appear on the diagonal and they're repeated a number of times measured by their multiplicities. Okay, so to do this in general, what you do is you build this big Hilbert space called L2 of mu m. And the way you build this is first you build a bundle of Hilbert spaces, H over the spectrum of S, such that the dimension of the fiber over the point lambda in the spectrum is equal to what the multiplicity function is telling you it should be. And then you can consider, once you have this bundle, you can consider sections, F, such that the value of F at lambda is in this Hilbert space H lambda. Since this is a Hilbert space, you can take a norm there. So this consists of the sections F from sigma of S into this Hilbert space bundle, such that the L2 norm of F is finite, and the L2 norm is defined by, first, you look at the norm of F at lambda in the Hilbert space where it resides, H lambda. You square that, that gives you a function on the spectrum. And then you integrate this with respect to the spectral measure. And we require that this is finite. That's the definition of the space of L2 sections of this Hilbert space bundle. Okay, so then the statement of the spectral theorem is that there exists a mu m and an isomorphism from your original Hilbert space where S is acting to this new Hilbert space, L2 of mu m, that sends an element x here to a function f, which f of lambda, let's call that phi of x. And over here, we have a new operator, which I'll call S bar, so the diagram commutes. And the operator S bar is fantastically simple. S bar of f of lambda is obtained by taking the function f of lambda and multiplying by lambda at each point. So remember, f of lambda is a vector at every point. You can certainly multiply it by a scalar, and it turns the operator on this Hilbert space into simply multiplication by lambda in a space of functions on the spectrum. And why is that intuitively plausible? Well, what we want is that f can be decomposed into eigenvalues, eigenvectors for S, and the eigenvector at the point lambda should be multiplied by lambda, that being the corresponding eigenvalue. So this is a complete statement of the spectral theorem. For unitary operators, we'll be working with a spectrum which will be a subset of the circle. But there's one nuance that's important to emphasize, which, as I said, S determines a mu and an m such that this is true. So you might think mu and m are invariants of S, but they're not. It turns out that there's lots of measures that give the same operator up to isomorphism. So S doesn't quite determine a measure. People call it the spectral measure, but it's not quite a measure. So let me just say, when two mu's and m's give you the same operator, so we say mu and mu prime are in the same measure class if mu of A equals 0, if and only if mu of A prime, mu prime of A is equal to 0. In other words, if they have the same sets of measures 0. What that basically says, for example, if they're probability measures, is that one is a function times the other, that nowhere, and vice versa, where that function is in L1 of each. And then the theorem is that mu m and mu prime m prime give isomorphic operators, or roughly speaking, the same operator, S and S prime, if and only if mu and mu prime are in the same measure class and the same sets of measure 0, and m equals m prime almost everywhere with respect to that measure class. Okay, so there's one thing I've swept under the rug, which is which sets are measurable. Remember, I said I was going to not talk about the sigma algebra of measurable sets, but I really should, because these measures floating around, which sets are they allowed to measure? Well, the answer is very simple. They should be allowed to measure the open sets of the spectrum. And more generally, the sigma algebra generated by the open sets, which are the Borel sets. Okay, so this is the idea of the spectral theorem. And the way we're going to apply it is we're going to take one of our measure-preserving transformations and get out of it these measures, mu and this multiplicity function m, and two objects are isomorphic, two measure-preserving transformations are isomorphic, only if these invariants are the same. So as a quick example, just to close with, if T of Z is equal to alpha times Z, where Z is ranging in the circle, alpha is in the circle, and T has infinite order. In other words, if T is an irrational rotation of the unit circle in the complex plane, then the measure is the sum of delta masses at alpha to the n over all n and z. In fact, this transformation turns out to be diagonalizable, and the powers of alpha will be its eigenvalues. And as a consequence, this will prove that, let me call this T alpha, that T alpha is isomorphic to T beta if and only if alpha is equal to beta to the plus or minus 1. So almost any pair of irrational rotations are actually distinct as measure-preserving dynamical systems. Okay, so I will post homework for due next Tuesday, later today, and we'll pick up on this spectral theory on Tuesday. Thanks, and I will leave the Zoom room open for anybody who wants to stay and chat or talk to other participants. And I remind you that there's a section tomorrow with Carl, and this is also a good place to meet up with people you might want to collaborate with if you're working on the homework. Okay.